Hello. Now we will discuss the topics of Simulink and also a different topic, symbolic math, two pretty much totally different aspects of Matlab with the focus on Simulink. Simulink is really interesting. For many of you, I think you'll really like it, and some of you will probably really hate it. It's something totally different, a different way of doing math than you've possibly ever done, unless you've been exposed to this in some other class. You've probably never approached things quite this way. The key is that you're actually drawing your equations rather than writing them out symbolically. And you're not writing the entire equation, you're writing out pieces of the equation, steps like add 5 or multiply by 10. Those steps are written out as input-output blocks, and when you put it all together, you have a set of linear equations, or you can even do nonlinear equations in Simulink. And it can be a whole system of equations, or it could just be one equation, but the point is you're never writing them out in the usual way with an equal sign. All you're doing is say this comes in and this comes out, or these two things come in, and that leads to this other output, like you might add two things together. But they're all just partial operations that then add up to the overall picture. And it's pretty interesting. You don't have to do any algebra. You just draw it all the way it comes, and you turn it on, and it hopefully sorts out the answer. Like I say, some people like it, some don't. It's a relatively new way of doing things. It's used a lot in certain areas of engineering, but it's certainly not a requirement anywhere. You can do everything symbolically if that's your preference, but it's nice to have seen it at least once. So the key is block diagrams. I'm going to teach you a little bit about block diagrams. That's necessary so you can actually use Simulink, which is all about drawing these diagrams and then just making it do the analysis. The blocks I'll show you, summation, which could also be subtraction, so subtraction or addition, scalar multiplication, which again could be times a fraction, so that could be your scalar division also. I won't do anything with matrices in Simulink, just scalars. Then you got input and output from the model, so you got constants or functions that come into the model. You have different ways of outputting stuff from the model, and I'll talk about that just a little bit. Then you can do all your calculus numerically on this tool. This is the first thing we're doing. Simulink is not an analytical tool. It's all numeric, but it will numerically integrate or numerically differentiate the signal that comes in. And I will show you a little bit of the nonlinear elements. I suppose this was originally created for linear systems, systems of linear equations or linear differential equations, but it also will solve nonlinear problems numerically. The examples, I'll go through 3 separate Simulink examples that are on the website, and starting from just pure algebra, which really isn't the strength of Simulink, but it shows you how the block diagrams work. And that's the assignment I've given you. I've given you an algebraic assignment, so definitely pay attention to that. Then I'll also show integration, just straightforward integration of a sine function. And finally, I'll show you how you could solve a complicated differential equation. It's a detailed example. Then that'll bring us to the symbolic math portion. There's one key function I want to just explain to you. This is not Simulink. This is back to the command window or your M files, and that's using the syms command, which defines Simulink to be using that quantity you've defined as a variable or a parameter that could be in the answer. So for example, if you wanted to do something with lines and you wanted M and B to be in the answer for slope and y-intercept, and you don't want numbers, you just want those letters, then you could define syms MB, and when it does the algebra, it'll actually manipulate that around as if it was doing algebra. I think the name of the software this used to be called was Maple, and it was absorbed into Matlab. It's kind of a competitor, an old competitor of Mathematica. It's not nearly as sophisticated as Mathematica, but it's got a little bit of the same things. All right, so let's talk a little bit about block diagrams and some of the tools that you'll see. The idea is that you have an input, and you can think of that as anything you want. I'm going to think of it as X. And then I go through a block. The first block I'll show you is called a gain block. Gain, just a fancy way to say scalar multiplication. And so let's say that's 5. Then if I'm thinking of this location in my graph as y, then what I've shown here with this little portion of the problem is y equals 5x is what that represents. Y is the output, x is the input. In between, I multiply by 5, so that's called a gain, scalar multiplication. And that's a basic block. We'll use quite a few of those. Then you have summation blocks. So for instance, on the one I'm going to show you, I'll have an input, like a number 3. That's an input to the system, so it only goes out. And let's say there's a plus next to that. And then maybe from somewhere else in the diagram, maybe I have a 2, and I'm thinking of this location as x. Then I come up and in, let's say maybe there's a minus sign here. All right, so this rectangular box I'm showing, that's a summation box. You can put plus or minus, so it'll either add or subtract. And then what comes out here, let's say I'm thinking of that as y. Then this graphical portion of my diagram is, and the summation in particular, is the equation y equals 3 minus 2x. And so I've done a portion of a linear equation, and then I could draw another summation box somewhere else. If I had x and y connected another way somewhere else, I could use another summation box. But this shows a part of the Simulink diagram. And the other block I'll show you right up front is there's actually a variety of output blocks. I'll show you a couple of them. There's like an XY plot that takes 2 inputs, x and y, and then you can double click on this plot to make it graph the x and y versus time, or actually x is the independent variable, y is the dependent variable, so it's y versus x is what that would graph. Then you could also create, there's what's called a 2 workspace output in Simulink, which I'll show you. And that is only an output also. There's only something coming into it, nothing coming out of it. And so you'll name, in here you'll just put a name, and that will be a way to send, let's say, x to your workspace as an array, and then you could do whatever you want with it using the regular Matlab tools rather than Simulink. Simulink's built on top of Matlab. And then the last, I think the last regular blocks I'll show you will be, well, I guess it's just one block, 1 over s. 1 over s takes an input that's some function of t, and it takes an output that is the integral f of t dt. So it's in an integration block. You do have to double click on this and put in an integration constant. You can do a derivative also, but I don't think I'm using that in this example. I'm just using the integration block in a later example. And there are some nonlinear blocks that I'll be using in another example. For instance, if you wanted to do x squared, that might not seem like a big deal, but that's actually nonlinear. There's like an x squared block where x goes in and x squared comes out. You can do that with a product block. There's a product block, that's supposed to be a time sign now, where 2 things could go in and out comes their product. So if x and y went in, x times y went out. That's also nonlinear operation, but Matlab Simulink does support that in the Simulink diagrams. All right, so let's take a look at the diagrams. Now to get to this, I had to type the word Simulink. You can see I've already done it. Type the word Simulink, S-I-M-U-L-I-N-K. And as soon as you do that, this is what will pop up. It's called the Simulink Library Browser. And it gives you a list of directories, and you can click on those different directories and different blocks come up to choose from. There's a lot more here than I can go into, but there's a lot of different tools that you can draw with. And then you say File, New, Model, and I already did that, and this blank screen pops up. It's a drawing palette. You're going to take devices from over here, grab them, plop them down into your Simulink diagram, and tell it to do an operation. So let's do a simple example of that, just using a single input and a gain. For inputs, those are sources. And let's say I want my source to be a constant. So I grab the constant block, and I'll double-click. When I double-click, I have the option to put in the value. So let's say I want my number to be 7. Now, inside this little block is a 7. It's got a tiny little arrow that needs to go somewhere. And so I'm going to run it into a math operation called gain. And then I'm going to simply display that answer with a sink. Sinks are the blocks that only have an input to the block. Nothing comes out of the block. And the simplest possible sink is display. It's only good for displaying constants, but that's what we have here. So I'll grab the display block. Now what I could do is grab these little arrows and pull it over, and then I can grab the next one and pull it over. So you can actually grab the arrows and manually drag them to where you want them to be, or you can click on the source block and then control click on the next block, and it'll wire it for you. And so by doing that twice, I've now drawn the 7 into the gain and then the gain into the display. Let's change the gain so it's 5. This is scalar multiplication, so the math should be 7 is the input, 5 is the multiplying factor, and then the display will be the answer for this part of the diagram. I'll just say start, simulation start is what I did. Under the simulation menu, there was a start option. I probably could have saved it first, but anyway, what pops up is in this block now it says 35. So all we've done is a very simple graphical description of 7 times 5 equals 35. Now let's consider a little bit more complicated thing. Let's say I had 2 inputs. I'm going to Control-C, Control-V to get a second constant. Let's say this second constant is 9. Now I've got 2 inputs, 7 and 9, and a math operation, addition. And I could combine that with a gain also. So math operation, gain. Pull this link back so now it's connected. I'll control click to connect everything. So now I've got 7 plus 9 times my gain, and this is a new gain, let's say 5 again. 7 plus 9 and then times 5. Simulation start. It says 80, so that was 16 times 5 is 80 is what that did. Not really anything useful yet, but you're getting hopefully the feel for how this stuff is connected up. All right, so now we're going to do a system of equations, and I'll need to go back to the pad here to explain this. This is the system of 3 equations we're going to do. If you look on the Matlab Lecture 5, you'll see this system of equations has been coded in Simulink. Now the thing is, this isn't the easy format to do it. Now I'm doing 3 equations for 3 unknowns. This isn't really the strength of Matlab, but it's a great exercise to show you how Simulink works. I've got x plus y plus z equal 2. That's the first equation. And similarly, I've got 2 other equations. They're all going to be simultaneously solved to find the combination of x, y, and z that solves all 3 equations at once. Now the thing is, those equations really are not in the best form. What I'd like to do is solve the first one for x, second one for y, and the third one for z. It's not the only way to do this graphically, but it's one easy way to graphically draw these equations is to solve each one for a different variable. So what I have here on the first equation was x plus y plus z equals 2. I'm going to write that as x equals 2 minus y minus z. And then in my middle equation, I'm going to solve that one for y. Y is equal to, and I had to divide by -2, so that's going to be -1/2, and then a parenthesis or bracket, -5 minus 3x minus 4z. I isolated y in the second equation. The third equation, I'm going to isolate z. That's z equals negative 1/3, and then I've got 3 minus 2x plus y. And those three equations are still the same three equations I started with, but now they're in a little bit more convenient form for drawing them. So let's go back to Simulink and draw those equations. I'm going to start, well, I'm going to actually use some of these same tools. I needed the constant blocks. I'll need 3 of those. So let me put those out here. The constants were 2, and then negative 5 in the second equation, and 3 in the third equation. I had 3 equations, so I need 3 summation blocks, and I have 3 answers, so I'll need 3 displays. Put out these summations or additions, and these displays, Control C and Control V. Now for the displays, I'm just arbitrarily going to pick which one is which. I'm going to call the top one X, and the middle one is Y, and the bottom one is Z. And then for my additions, let's just do one equation to start with. This was the equation 2 minus y minus z. That's a plus. I double-clicked on the summation block, and it gives me a chance to change the signs and add new signs. I want it to be plus, minus, minus. So now there's actually 3 input ports instead of just 2 input ports. And I want my 2 to go into the first one, so I'll control-click. Now I've got a 2 in there. And after I get done with that calculation, that's going to be x. The y and z need to be added in there too. I need a minus y and a minus z. Now this portion of my graph, there's a portion of my graph that's y. Right here is y, and then down here is z. I need to do something so I can draw my arrow back to those. I'm going to get a gain. That's a math operation. I'll need a bunch of these gains, actually. But right now I'm just going to put 2 out. All right, now I have something to connect back to. The middle arrow, there's no control clicking here. You have to drag it backwards. At least I don't know a trick for doing this any easier than that. All right, I drag that arrow so that now when my area that I'm thinking of is y will go into the x equation, the first equation. And I'll do something similar for the next one down. I'll drag it all the way down, and that connects to my z. So now what I've done is I've actually completed the first equation. I have 2 minus y minus z equals x. And one thing you might have noticed is that I have a bridge here. Where I dragged my line back all the way to z, I had to cross the y line. But there's not a heavy dot. You can tell it's a bridge because there's no heavy dot. Where it's a split, there's a heavy dot showing that the information is going both directions. And now I'm ready to do the other equations. They're a little more complicated. The second equation was negative 5 minus 3x minus 4z. So that was actually plus minus minus again. The negative 5 goes in first. And that output is going to go through this gain. I had a negative 1/2 in front. So for the gain, negative 1/2. Matlab will take the fractions as inputs. No truncation. When I first did it, it had a little k there. K is Simulink symbol for I don't have enough space. So I made my triangle a little bigger, and then I was able to read the number negative 1/2. All right, so that's the constant in that second equation. The next thing was a negative 3x. For that, I'm going to need a gain. I'll put it up here for my x variable. I think I'll put it way up here. And I want it to flip, so I'll right-click, Format, Flip Block. Now it's pointed the other way. That just keeps my arrows from being quite so tangled. All right, now that gain is a negative 3 from the equations I showed you before. Drag that around and over to the second slot in my second equation. That's a negative 3x. And then I need one more gain like that for my z variable. And that is a, well, I just accidentally doubled up on my minus signs. That should have just been a 3x because I already had a minus sign. And this new gain should be a 4z. There we go. So now I've done the second equation. That's negative 5 minus 3x minus 4z, and then take that quantity times negative 1/2, and that's going into my y output. And now one last equation. This is plus minus plus. The third equation had a 3 going in. And then the gain, after I get done combining those three things, is going to be negative 1/3. Stretch it out so I can see that it says negative 1/3. And that'll be my z. To fill in these last two holes, I need a negative 2x. And I can do that with a gain up here. I'm running out of room, so you can actually grab a whole bunch of things at once and then drag the whole thing to give yourself more room. All right, so I drag that back, change the gain so it's a 2, and then control click. It'll wires it all the way down to the second spot in the third equation. And then finally I have a plus y, so I could actually just drag this arrow back. I don't need a gain. Just got to get all the way back to the y location. All right, so now coming from y, I go in. Now let's double check. That's 3 minus 2x plus y. And so that looks like it's the whole, that's all the arrows are connected. If I didn't make any sign errors, then it should give an answer. And when I did simulation start, and what it did is just solves it. It's 3 equations, 3 unknowns. I drew the 3 equations, 3 unknowns, and said go, and it figures out what the 3 values x, y, and z are. It says 1, 2, negative 1, which I think is the correct answer to this system of 3 equations. So that's pretty cool. It's not a practical use of Simulink by any means. You have much easier ways to solve 3 equations for 3 unknowns. But the point is I drew a nasty system of equations, and I said go, and it just figured it out. So that's pretty nice. All right, so let's start a new model and do something different. In this model, I'm going to do a simple calculus problem, just an integration of a sine function. I'm going to need a sine function, and that's a source sine wave. If I double click on that source, I have various options. I can change the amplitude, frequency, phase. I'm going to just change the amplitude to 2. I'll leave the frequency alone, so that means it's got a frequency of 1 radian per second, a period of 2 pi. All right, so there's my sine wave, and I'm going to integrate that using another math. Actually, it's in the continuous library. In the continuous library is the integrator, 1 over s. And it won't do to send this to the same sink that we had. It needs to go to some other kind of a output. And I have a couple choices that would be good. I could send it to the workspace, and I'll do that in a second. Before I do that, I'm going to send it to the graphing tool, which is plot, I think. Where did it go? Oh, I'm under source. I'm supposed to be in sinks. There we go. Under sinks, there's different plots. There's scope, but what I want actually is XY graph. So I'm under sinks, XY graph. Now I don't want the sine wave to be my, or the integration of sine wave to be my x value. I want it to be the y value. What I want for the x value is time, so I needed the clock. Clock, there really is no x. Simulink all about integration with respect to time. So clock is going to be the x value, the horizontal axis, and then the y value will be input from the sine function, or actually the integration of sine for this plot. And I do have the option for an initial condition. And when I double click on 1 over s, I can put in the initial condition. I'll leave it at 0 for just a moment. And I think that should do it. I need to pick the amount of time I integrate for. There's a simulation stop time. 0 to 10 seconds is good enough because this sine function has period 2 pi. And so I'll start it, and we probably won't be able to see very well because I didn't set the graph limits. So we're just seeing a tiny piece of the graph. Let's double click on XY graph. X is my time, so I'm going to start at 0 and go to 10. It didn't automatically scale this, which was kind of an annoying aspect of this graphing tool. And my Y value, I'll go from 0 to 4, I think, is what I want. Let's say -2 to 4. And then start it again. There we go. What you have is a sine or cosine function. It looks like it's an inverted cosine function, and it's an average value of 2. Now, if I had put in an initial condition of two, let's say -2, there we go. I'll put in an initial condition of -2 and start it again, and now it looks a little more normal. It's the negative of a cosine function. And if you recall from basic calculus, the integration of sine is negative cosine. So that's what we're seeing now. As long as you had the right integration or constant, then it works. And one other thing, this isn't really a very good graphing tool. It's not the best for me. I'm not real happy about doing it that way. For my sync that I prefer, I usually use this sim out device. And there's a couple ways you can do it. Maybe the simplest is to double click, and by default it's set up to output a structure. But I'm going to change that to array, and I'm going to name it. I'm going to call it input, I-N-P-U-T, and draw that back to my sine wave. Now I'm going to copy that block, Control-C, Control-V, and drag it back to just past the integrator, and I'm going to call that output. And then I'm going to copy it one more time and drag it back to the clock, and I'm going to call that time. And what's going to happen is that this is going to send three different arrays back to my workspace. I'll run the model. I get the same plot just like I did before, but I'm not worried about that. Instead, I'm going to go back to the command window, and if I look in my workspace, I now have input, output, and time, 3 arrays with 51 entries in each. And so those are new. Those were just created by Simulink. And for instance, I could then say plot, time, comma, input, comma, time, comma, output. You have to, the syntax there is x, y, x, y. x1, y1, x2, y2. And now we see 2 plots pop up. The first one is the sine function, and then 90 degrees out of phase from that is the integration of it, negative cosine of time. So it's sine t and negative cosine t is what we're seeing plotted there. So that shows that it can do the integration. it's really not doing, as far as I know, it's not doing much at all symbolically or exactly. What it's doing is numerically, here we go. It's doing it numerically using tiny little steps. And you can control how small the steps it uses in the numerical integration. You can specify how the tolerance of that integration. The smaller the steps, the better, but maybe if you get carried away with that, it can take a long time to calculate. So anyways, there's numerical integration. And then on the website, I included one other example. And this is a pretty imposing looking plot. This is included on the website. You can download this. It's called stark.mdl. And I want to take a moment to explain that problem. It's described on the website also. The differential equations that you'll see there are two equations describing the motion of a particle. And the original Stark effect was named for if this was let's say a proton, and here is an electron, a tiny little electron. And way back in the late 1800s, late 1800s, they thought that they knew there were electrons, and they knew there were positively charged nuclei, and so they thought that atoms kind of were like little planetary systems. Thought that was pretty cool. There's this attractive force they knew about, and the attractive force was 1 over r squared. It went as 1 over r squared just like gravity does, so they thought, wow, this Coulomb attraction creates a little planetary system. It's the same math. Isn't that neat? And this electron, it's going to go in an orbit, and we know that the orbit will be circular or elliptical, or it could be hyperbolic if it's on an escape orbit, but it's going to act like a little planet, is what they thought. The equation for that was the force is some constant times the two charges, q1, q2, divided by the distance squared. And that's similar to how gravity works. It's 1 over r squared for gravity also. It depends on the two masses. So anyway, that seemed pretty neat, and they wanted to study this a little bit. So the formula for that force, that attractive force on the electron, depends on the xy location, where let's say the nucleus is at the origin, and this is a triangle with a height of y and a base of x, and so the cosine and sine of that angle there would be x over r would be the x component of this attractive force. You take that times a constant divided by r squared, and you get, and put a negative sign, and that's the x acceleration, what I'll call x double dot. So that's this x over r, that's a cosine of an angle times k over r squared, you get the x acceleration. You'd have to divide by the mass, but that would be in the constant. The y acceleration is similar. It'd be the sine of an angle minus y over r times k over r squared. That's equal to the y acceleration, y double dot. Now this looks like two separate equations that aren't related until you remember that r squared is equal to x squared plus y squared. And so these are actually coupled equations. And no big deal, this is basically the same math that Newton and Kepler and them all solved to figure out how planets move. So they knew exactly what the solution to this would be when they started. But Stark and other people thought, well, now wait a second. If I'm an electron and I'm orbiting the origin, well, there's going to be forces on me besides the attractive force. Very typically, there could be this small little force, let's say in the x direction. At any point in my orbit, maybe even if I'm over here, I still have that force on me. Wherever I'm at in the orbit, I have that little force to the right. And that makes sense because if you think about it, electric fields do push electrons. But it wouldn't push it very much, not enough to make it get knocked out, because this attractive force would be way larger. There's a large attractive force and a tiny little force to the right. They just wanted to know, what would that tiny little force do to the shape of the orbit? How would that affect the electron behavior around the nucleus? Here's the nucleus at the origin. What's that going to do? And that's a very reasonable thing, because there's electric fields throughout the universe. Every electron is going to have a little force pushing on it, and because electrons are so small, those electric fields are going to seem like constant forces, small constant force pressing in one direction. And so they were very curious to see what happened. And so in the math that I've programmed, I've made one change. instead of saying that the x acceleration is negative kx over r cubed, that's what it would be if it was just regular problem, I've added a plus a constant called c. And c is a small number, much smaller than this attractive force. But it's always on. And then the y equation is unchanged, negative k y over r cubed. I went ahead just for simplicity and made k be 1, and I made c be 0.001, something like that, a very small number, so 1,000th of k. And I picked r to be 1, and I picked regular numbers. It doesn't affect the general behavior of the solution. It shows you very nicely the character of the problem. So let me show you the Simulink diagram for that. This is a problem you would not solve in DiffyQ because it's probably too hard for your DiffyQ class, but it is the same subject that you study in DiffyQ. It's pretty much a numerical problem. You can't easily solve this one by hand. There's not any easy solution available. It's really, even though it's not what's called a chaotic problem, it does have a solution, but that solution generally has to be found numerically. It's just too messy otherwise. So you code it, you draw it. You can look at this, you can download this and look at it on your computer. Pretty much, I just wanted to show you that I got the integrations in there. I'm calling this part of the graph x. Working backwards from that twice, I must be looking at the x velocity, and then one more step, that must be the x acceleration. If you go backwards from position through an integration, well, that's derivative. And so x dot or x double dot. That means that this top middle spot on the diagram is the x acceleration. I've got a summing box to add the small force to that other term, the negative k over r cubed, negative kx over r cubed. And this math in the middle does that nonlinear business, the business of x squared plus y squared square root to get r. That's a nonlinear bit of math, but the tools are all there in Simulink to do that. So I just drew the equation. It really didn't take long at all to draw it once you know this tool. And now I can run it. And you see something kind of odd. It's actually running right now. I've made the step size really small so that you can watch it calculate. And what you're seeing is right there in the middle, that's the nucleus. And the electron's getting closer and closer to the nucleus. The orbit started out as a perfect circle, actually. And the numbers got so that it flattened. The force is to my right, which means that it's pushing one way, but it's getting oblong in the other way. It's becoming more and more elliptical, and eventually it gets so elliptical that it's just basically a line segment. And that line segment the electron would crash into the nucleus, according to this model. And it's kind of interesting and shocking to the physicists. It's really a very simple proof of why electrons are not little planetary systems, or not like little planets. They don't obey those rules. They don't obey Newton's laws. They obey the laws of quantum mechanics. So that was an early proof that of how electrons are different. It is a really interesting model still for another reason. I actually learned about this model with regard to satellites. This is a very nice explanation of why satellites crash. The satellites are in the same kind of orbit. They start out in a nice circular orbit. They're pretty high up, so atmospheric drag's pretty small, and they should never crash. But they're also being bombarded all the time with particles from the sun, just like this problem. They're always being, and over the scale of a month or whatever, the Earth doesn't really move that much. So pretty much the force from the sun, even though it's very small, it's always in the same direction, and it tends to decircularize the orbits. They get less and less circular, more and more elliptical, and one end dips down, one end goes up, the other end goes down, and that one that's going down is starting to dip into the atmosphere. And when it starts dipping down, now it gets hit by a whole bunch of drag, which steals a lot of energy from the orbit, and that's just after that, it spirals in and crashes, but a lot faster than it would if it wasn't for the solar radiation pressure. So that's kind of an interesting thing about that Stark effect model. So that's probably more than you wanted to know about Simulink. Let's go now to the Matlab command window. Oops, here I am. And we're going to start something new. I'm going to clear all. And I want to try just a real simple thing with the symbolic math. Let's say, as a real simple case, I said SYSM, and I'll say A space B. SYMS. SYMS AB. All right, now A and B are symbolic variables, which means they can be part of any answer. if I say, I've not given a or b a value, I just did clear all before I started this, but if I say x equal 2 times a, it says, okay, x is 2 times a. If I say 5 times x, well, it says, well, that's 10a. So that's really cool. That's a symbolic, that's pretty simple, but it's a symbolic thing. X is 2a, 5x must be 10a. That's a simple example of how I've stored that a that can be now part of any answer. And I can do mathematics. I can use some of the functions in Matlab with that option now. And so what I did as a simple example is I solved two equations for two unknowns. On the website, what I did was I defined C through F to also be symbolic. Let me do that. S, Y, M, S, C, D, E, F. All right, so A through F are now symbolic variables. And I'm going to make a matrix, capital A, which is A, B, semicolon, C, D. I put them all into a 2 by 2 matrix, A, B, C, D, and that stands for AX and BY. I need a right-hand side, call it capital B. That will be E semicolon F. And so what I'm now doing is I've set myself up to solve the equation AX plus BY equals E and CX plus DY equals F. There's no numbers there at all, just 6 letters representing what normally would be numbers. And then I want to solve for X and Y. So that means I need to inverse the A matrix, take it times the B matrix. INVA times B. And I get a whole bunch of stuff, but actually that is just 2 numbers. The top row is X, written symbolically using those 6 parameters that we defined. And the bottom row is a single number, Y. You can even eval these. There's an eval function that allows you to put numbers in for those and turn that formula into a number. So that's pretty cool. So you can do symbolic work. It's really not MATLAB's strength, but it's an option for you. Other things, there are solver tools. For instance, I have an example here for dsolve, which will solve a simple differential equation. Let's consider the differential equation y dot plus 3y equals 0. That's what that is. It says y equals dsolve, and then this is actually a string. MATLAB's going to parse through that string and figure out what equation you're trying to teach it. Capital D stands for derivative. So when I say capital dy, I mean the time derivative of y plus 3y equals 0. That's a simple equation you should see in Calc 1 or Calc 2. And it worked for a minute, and then it says, oh, okay, well, I know what y is. Y is C1 times e to the negative 3t, which is the solution to that equation. Then if I wanted to have an initial condition, I can add that in instead. The initial condition goes in as a separate string. I've done the same differential equation, but now I say y0 equal 2, and it's smart enough to figure out that integration constant C1 should be a 2. So y equals 2e to the negative 3t is now the solution to that simple equation. To solve this by hand, you use separation of variables. It's something you learn really early in DiffyQ, or you also, this is really just a straight integration, so you really learn about this when you learn Calc 1. But the point being, it's not this specific problem, but just that there are some tools, there are some functions in MATLAB that return equation answers. I think MATLAB's more of a numerical tool. It's for finding out numbers to problems or getting graphs for equations rather than actually getting the equation. But it does have a few analytical tools if that's interesting to you. So that's it for this talk. Thank you.